IEEE International Conference on Distributed Computing Systems, PerDNN Offloading Deep Neural Network Computations, Pervasive edge servers. Seoul National University. Abstract: emerging mobile applications such as cognitive assistance based on deep neural network (DNN) require low latency as well as high computation power. To meet these requirements, edge computing, also called fog computing, has been proposed, which offload computations to edge servers located near mobile clients. This paradigm shift from cloud to edge requires new computing infrastructure where edge servers are pervasively distributed over the region. This paper presents PerDNN, a system that executed DNNs of mobile clients collaboratively with pervasive edge servers. PerDNN dynamically partitions DNN computation between a client and an edge server to minimize execution latency. It predicts to next edge server to the client will visit, calculate a speculative partitioning plan, and transfers the server-side DNN layers to the predicted server in advance, which reduces the initialization overhead need to start offloading, thus avoiding cold start. We do not incur excessive network traffic between edge servers, though by migrating only a tiny fraction of the server-side DNN layers with negligible performance loss. We also use GPU statistics of edge servers for DNN partitioning to deal with resource contention caused by multi-client offloading. In the simulation with a human trace dataset and execution profile of real hardware, PerDNN reduced the occurrence of cold start by up to 90%, achieving 58% higher throughput when clients change their offload servers, compared to a baseline without proactive DNN transmissions. Introduction: future mobile applications such as augmented reality first, cognitive assistance second, and cloud gaming third require not only intense computations but stringent latency constraint. Since cloud services in distant data centers have difficulty in meeting the latency requirement, the new computing infrastructure called edge servers are also called cloud-edge or fog node FIFs has been proposed, which offer high bandwidth, low latency access to storage and computing resources at the edge of the network. Wi-Fi APs or small cells. IEEE recently adopted OpenFog reference architecture (OpenFog-RA) as an official standard, which describes a general architecture that distributed computing servers closer to data sources such as IoT devices. OpenFog-RA presents the sketch of a large-scale edge network composed of multiple interconnected servers installed in smart cities. One possible form of such a network of public edge servers, a cluster or hierarchy of edge servers that perform computations of user application in public places, for example airport or subway. A key attribute of public edge servers is versatility, which can perform general computation of any authorized client, enabling pervasive computing environment for user running various applications. This is in sharp contrast to private edge servers, which provide a set of pre-installed services only a few clients, resulting in limited use of edge servers. A promising application of public edge servers is to offload computations for deep neural network (DNN), which has great model diversity as well as high computation requirement. For example, mobile cognitive assistance (MCA) helps blind people by recognizing objects seen by wearable glasses and telling the object to the owner. Recent techniques for object recognition use compute-intensive DNNs 8 and 9, so such a service can offload the DNN computations to a nearby edge servers, improves per app performance and energy consumption of wearable glasses. An important aspect of DNN is that they can be modified or replaced after deployed. If MCA needs to recognize a new object, for example a newly family member, it may require new model structure with additional output level and retaining with the new dataset. Also, the model can continuously train using locally collected data to specialize in the target environment. 10. These situations require each client to have its own model trained by the client's specific task and data, which heighten the need for versatile edge servers where clients can dynamically deploy their custom DNN models and offload executions. The purpose of this paper is to explore the feasibility of such public edge computing systems for running users' custom DNN models. There are two primary challenges to achieve high and stable performance when offloading DNN computations to public edge servers. First, we need to deal with the performance drop of DNN offloading. A cold start for new edge servers. To offload DNN execution to a new edge server, the DNN model has to be first deployed to the server, which significantly delays the time to start offloading. Although runtime provisioning of edge servers has been extensively studied in edge computing communities 11, 12, and 4, they mainly focus on optimizing the migration of VM or container, not DNN models. A recent work named Ion 13 mitigated the performance drop by incrementally transmitting DNN layers and by partially offloading the execution of the transmitted layers. S3 suffered from low performance during the initial stage of model transmission. See section 2.b. Secondly, whenever a client offloads its DNN computations, it should offload to the best edge server among the nearby ones, considering many dynamic factors such as workload or of edge servers of network status to minimize DNN execution latency. This is especially true when multiple clients simultaneously offload DNN computations to a single server, so the server might suffer from GPU contention, which affects the DNN execution performance. To tackle those challenges, we proposed PerDNN, a system that manages the offloading of DNN execution between mobile users and many interconnected edge servers. PerDNN selects the best edge servers to offload DNN execution using a partitioning algorithm based on runtime stage such as GPU height statistics of edge servers and network conditions, as well as hyperparameters of DNN models. After edge server selection, PerDNN dynamically deploys the user's DNN layers to the edge servers and executes the DNN models collaboratively, partially at the client and partly at the server, to minimize the DNN execution time to avoid the cold start that occurs when a user moves to a different edge server. PerDNN periodically predicts the next edge server visited based on the user's recent trajectory, calculates a speculative partitioning plan between the client and the predicted server, and proactively migrates the server-side DNN layers of the plan to the next edge server. This allows the user to immediately start offloading DNN execution when visiting the predicted edge servers. To reduce the network traffic, we select and migrate only a fraction among the server-side layers for cloud edge servers with heavily network traffic, which sharply cuts the network traffic with negligible performance degradation. To our knowledge, PerDNN is the first study to 1. Exploit GPU information for DNN partitioning and perform real-time proactive caching in the context of edge computing. To evaluate PerDNN, we simulate edge computing scenarios where more than 100 users offload DNN computation to edge servers dispersed in a smart city while they are on the move. For simulation, we use two-person source mobility datasets collect from Beijing and KAIST and execution profiles of real embedded board real embedded boot and desktop servers using the linear SVR models, which shows high accuracy among various trajectory prediction algorithms. PerDNN predicted the next move of the client and proactively transmitted their DNN layers to the edge servers around the predicted location. It reduced the occurrence of cold start by the 70 to 90% and achieved 58 to 97% higher DNA query throughput when mobile users change their offloading servers compared to baseline with no proactive transmission. Also, we could reduce the 43 to 67 of the peak backcore traffic needed for proactive migration by migrating a fraction of the DNN model for crowded servers with 1 to 2% of performance loss. The rest of the paper is organization as follows. Section 2 introduces the background and the motivation of this paper. Section 3 describes the design and implementation of PerDNN. We evaluate our system. Section 4 surveys related works in Section 5. And the conclusion in Section 6. In this background and motivation, in this section we give brief explanation on DNN and introduce a cold start issue raised when offloading DNA execution to public edge server. The neural network. DNA is organized with DNA layers. Each DNA layer receives input tensors from the previous layers, performs each operation, and delivers the output tensor to the next layers. The DNA layer contains two types of parameters. One is hyperparameters, whose values are fixed during trained DNN model, and the other weight, whose values are updated by running algorithms. Gradient descent. With training data, the training of the DNN model requires a massive amount of memory and computational resources, so it is usually performed in cloud data centers. The trained DNN model is deployed to client and used to infer outputs from new input data. In this paper, we only deal with offloading of DNA inference, which has a direct impact on user experience in mobile applications. Overhead of deploying DNA models. To offload DNA execution from a client to an edge server, the client's DNA model has to be represented in the server. Commercial edge computing solutions of major cloud providers, Amazon Greengrass, Microsoft Azure IoT Edge, Google Cloud IoT Edge, let users save their DNA models in the cloud and make edge servers download the model before executing it. However, since modern DNA models for complex tasks typically consist of numerous weights, a user likely will wait for a quite long time to download full DNA models. For example, in Inception 21K9, a popular DNA model for image classification with a size of 128 MB is completely downloaded in 80 seconds under the global average download speed 57.91 Mbps, which is hardly tolerable for today's mobile users. The high overhead of mobile model deployment makes it difficult to offload DNA execution to public edge servers on demand, especially when the user moves frequently. A recent study named ION mitigated the waiting time for model deployment partitioning a DNA model between a client and server by incrementally uploading the server-side layers from the client to the server. ION assumed that a model is saved in the client and uploaded to the edge server for offloading. ION partially offload the execution of uploading layers before the fully model transmitted, so DNA execution performance is gradually improved as more layers are uploaded to the server. The deployment strategy improves DNA execution performance during offloading DNA layers, but initial initial performance remains low when a client just starts uploading DNA layers, as the client has executed most of the DNA layers by itself. Figure 1 demonstrates the performance drop of ION, which happens when a client starts to offload DNA computations. to a new H server. We measure the execution times of 40 consequently generated DNN queries on inception 21K. 9 each query was raised 0.5 seconds after the previous query is DNN execution time while user moves from one H server to another. Executed. The client devices was embedded board OD, RIOD, and the server was a desktop PC equipped with a high-end GPU, Titan XP. For the first query, the client executed all DNN layers at the local devices as no layers has been uploaded to the H server yet, so execution time was quite high. DNN execution time decreases as more layers were uploaded, but soared at the 21st query, where the client changes its offloading server. Although DNN execution time decreases again rapidly due to incremental offloading, the spike of execution time at the start of the offloading would harm users' mobile experience. For example, frame drops in video analytics whenever a user moves from one H server to another. Mobile users who frequently change their targets H servers would especially be vulnerable to the fluctuation. Proposed offloading system PerDNN. In this section, we presented the design and implementation of PerDNN, which reduces cold start by predicting the movement of mobile users and predictably migrating DNN layers to the next H server to visit. We first describe our H server environment and the overall architecture of PerDNN. Next, we delve into how we predict the next H server and partition a DNN model. H server environment. Figure to illustrate our H server environment. We considered a general wireless local area network WLAN where mobile users connect to nearby Wi-Fi APs in the public places, for example, cafe, street, or office. Next, we envisioned the H server infrastructure integrated with WLAN, where computing nodes equipped with accelerators such as GPUs are located near the hotspots. The H server of each hotspot routes data between the users and the nearby computing node, so hotspot users can access the computing node with low latency. H servers are interconnected through backhaul network, which has been used for file caching 18, 19, or service migration 11. In this paper, the backhaul network is used to transmit DNN layers between H servers. A hotspot client, small glasses in figure 2, can offload DNN execution to the computing node after deploying its DNN models of layers to the node. We assume the model is uploaded from the client to the node EON 13, but it is also possible to make the node download the model from the cloud. The H server environment based on Wi-Fi APs. When the cloud moves to another hotspot, it can either offload DNN execution to the new computing node in the current hotspots, as previously over 2. Second, keep connection with the previous server and route input and output data through backhaul networks. In this paper, we focus on the first case, because routing leads to suboptimal offloading with increased latency and consumes backhaul traffic while the client offloads computations. It should be noted that despite these backhaul drawbacks, routing can be useful in some cases, for example in load balancing 20, but we leave the possible as the future works. Overall architecture. Figure 3 shows the overall architecture per DNN. The proposed system consists of a set of interconnected H servers and master servers, which controls the deployment and the collaborative execution of DNN models. The system works as follows. When a mobile client first connects to one of the H servers, it uploads two types of information to the master server, DNN profile and current trajectory. DNN profile includes the type of hyperparameters of DNN layers, which are used to partition a DNN model. DNN profiles does not contain the weight of layers, the heaviest part of DNN model, so it can quickly upload it to the master servers. Currently, trajectory is the recent location of the client during a certain time period gathered from GPS or Wi-Fi positioning system. The client periodically transmits each quarterly trajectory to the master server, so the master server can keep track of the latest trajectory of the client. Using the DNN profile and the current trajectory of the client, the master server controls the following actions. First, a collaborative DNN execution and proactive migration of DNN layers to the next visited H servers. Collaborative DNN execution. DNN practitioner in the master server creates a partitioning plan for the client, which specifies the execution location of each DNN layers and how to upload the DNN layers. DNN partitioning is further explained in the section 3.c. The partitioning plan is delivered to the client, and the client incrementally uploads the DNN layers to the edge. Overall architecture of proposed system. Server according to the plan when a DNN query is raised. The client executes layers one by one until the execution reaches the upload layer, and sends the input of the upload layer to the H servers. The H server executes the upload layers and returns the result to the client. The client continues to execute the rest of the layers, if any, since the partitioning plan is used to current DNN executions. We call the plan current partitioning plan proactive DNN migration, while the client, the H server, collaboratively executes a DNN model. The master server predicts the location of the client using the client's current trajectory. Then each find H servers around the predicted location by finding nearby hotspots in the Wi-Fi database such as Winger, under the assumption that the master server has a mapping between H servers and the Wi-Fi hotspots. The master server then creates partitioning plans for the H servers near the predicted location. These plans are delivered for future executions, so we call them future partitioning plans. The server-side layers of the future partitioning plans are transmitted from the current H server to the corresponding H servers. If the current H server does not have all of the server-side layers, it sends layers as many as possible, so client can upload only the rest of the layers when it visits the predicted server. After receiving DNN layers, H servers keep the layers for containing durations, TTL, time to live, and discard them after TTL is received when another server attempts to send the DNN layers of the same client to the server. So the layers already existing at the server are not sent again, thus avoiding duplicate transmissions. PerDNN periodically repeats the above process to update partitioning plans according to the runtime stage and keep sending DNN layers to the H servers near the mobile client. When a client visits the H servers, PerDNN creates the current partitioning plan as mentioned in section 3.b.1. It should be noted that the plan is based on the current runtime stage, server workload, and network conditions, so it might be different from the future partitioning plan made previously, proactive migration to this server. If server already received all parts of the server-side layers from other servers, the client can immediately start offloading the execution of these layers. If there are missing server-side layers, the client will upload the remaining layers to complete the current partitioning plan. If the server does not have any server-side layer of the current partitioning plan, the client incrementally uploads the server-side layers from scratch. Interestingly, we found that migrating only a tiny fraction of the server-side layers can improve the performance substantially, which can exploit to reduce the network traffic. Section 4.8. DNN partitioning, GPU-aware execution time estimation. The objective of DNN partitioning is to create a partitioning plan, which determines the execution location of DNN layers to minimize execution latency. Previous studies on DNN partitioning 22 have already introduced algorithm to find the best partitioning plan with minimum execution time based upon the estimated execution time of each DNN layers and the time transmission tensors. So far, however, no previous study has considered the congestion of GPU, which is critical to DNN execution performance. When partitioning a DNN model does having difficulty when multiple clients simultaneously offload DNN execution to an edge server equipped with a shared GPU. PerDNN uses GPU information when estimating layer execution time, so it can derive a more accurate partitioning plan than previous approaches in case of multi-client offloading. However, building an estimation model for layer execution time is extremely challenging because it is affected by numerous factors. While server concurrently executes DNN inference on multiple clients, the execution time is influenced by interface in shared GPU or system resources such as streaming multiprocessors, GPU memory, and PCIe bus. Various GPU sharing schemes, temporal sharing, Trinity special sharing, or hybrid of them, make it more difficult to predict the execution time. Estimating layer execution time considering all these factors is extremely complicated and feasible in general. Therefore, we take practical approaches that does not require any prior knowledge of hardware details of GPU scheduling policies but use GPU information to estimate resource contention. PerDNN predicts layer execution time based on GPU statistics as well as layer hyperparameters. We assume edge servers can measure GPU statistics, including kernel memory utilization, GPU memory usage, and GPU temperature without significant overhead. So before deriving partitioning plan, the master server pings to an edge servers to obtain current server workload, then estimate layer execution time using the execution time estimator of the server based on current server workload. The execution time estimator of each edge server is trained offline using the data generated by profiling the execution. Kernel memory utilization and GPU temperature was measured by NVIDIA management library. Kernel memory utilization means the percentage of time spent on kernel execution of memory operation over the past sample period between 1 second and 6 per 1 second. Mean absolute error of the execution time estimation with different server workload. Time of the DNN layers while concurrently running a DNN inference issued by multiple clients. During the profiling, server workload is changing adjusting the number of clients. We extend the per client in NVIDIA TensorRT inference server to control the concurrency level and measure the execution time. At the same time, the server records its GPU statistics whenever receiving a DNN request from a client. Using the dataset, the edge server trains random forest models for each layer types, convolution, FC, and etc. Then predict the execution time given the server workload and the layer hyperparameters. Figure 4 shows the mean absolute error (MAE) of the estimated execution time for convolution layer. For comparison, we explored the MAE of the estimation model of the latest approach, neurosurgeon, which only used the layer hyperparameters to train linear and logarithmic regression models represented as LL. Different models were trained for each server load number of clients as described in their paper. The result shows the MAE of LL surges as the number of clients increases. The MAE of the single layer is significant at most 800 US, but modern DNN models often use hundreds of layers, so the aggregate error of the entire model would be substantial. To test if the GPU information improves the estimation, we trained the same error models but with the GPU statistics as well as layer hyperparameters represented as LW server load info. Error server load info shows much more MAE than error when main client send a request, which implies that GPU information is useful for estimating layer execution time under heavy workload. Our method RFW server load info shows even less MAE than error server load info, suggesting that our random forest is better than linear logarithmic models to run the nonlinear relationship between execution time and workload features of client kernel memory utilization, GPU temperature. The right side of figure 4 shows the importance of each feature in our random forest 27, indicates that the workload features were more important than layer hyperparameters when estimating layer execution time. Partitioning algorithm. Given the estimated layer execution time, the optimal partitioning plan leading to the minimal execution time can be found using the graph-based partitioning algorithm. 13. Figure 5 illustrates the algorithm with an example DNA composed of two layers. The DNA is transformed a directed graph which expresses the data flow between a client and the server during DNA execution. The blue and yellow node indicate client side and server side node respectively. Edge weight, which represent the time taken for layer execution and data transfer, and determined as follows. Server side layer execution time is gained from the execution estimator of the edge server, as explained in section 3.1. Client-side layer execution time is gained from the DNA profile. Input-output transport time of each layer is calculated by dividing the input-output size saved in the DNA profile by running runtime network speed. Since the sum of the edge weight on the path from the input to the output is the time executed the DNA model. The fastest execution path is the shortest path from the input to output. In figure 5, shortest path red rows indicates that running layer A at the client layer B at the server is the fastest way to execute the DNA. By applying the algorithm to all edge servers visible to the client, the master server can find the best edge server with minimum execution time and the corresponding execution locations of the DNA layers, which is the current partitioning plan. Since the layer execution time of each server is estimated considering the GPU statistics, the workload automatically balanced. Crowded servers with long execution time would not be selected for offloading. To derive future partitioning plans for proactive migration, the master server applies the same partitioning algorithm to the edge servers within the certain distance, 50 meters or 100 meters in our evaluation. From the predicted location, we use the current GPU workload to estimate the execution time for future partitioning plans, under the assumption that the GPU workload of edge servers do not change abruptly in closer futures in less than 30 seconds as determined in section 3D. The server-side layers are proactively migrated to all edge servers within distance, so that the client can immediately start offloading when visiting one of the servers. After the execution location of each layer is determined, we need to decide the order of uploading the server-side layers. For example, which layers should be uploaded to the servers first. Our strategy is send the layers with high offloading benefits first. We defined the efficiency of layers as the latency reduced by the offloading layers divided by the size of the layers. We create partitions of the server-side layers, which are all the possible successive layers in the server-side layers, and calculate the efficiency of the partition. Then we decide to upload the partition with the highest efficiency first and update the efficiency of the remaining partitions. The same process is repeated until all server-side layers are uploaded. We use the same algorithm for proactive migration as well, to determine the order of sending layers from the current edge servers to the next edge servers. This efficient-based algorithm makes the next edge servers receive high-efficiency layers first, so that the client can offload the execution of those layers even though the whole server-side layers were not transmitted yet.